Time for even more fun. But you don't believe me, it's even more fun. Quadratic and power models. Now again, all that we're really looking at here is real live data and trying to determine what type of function it is. The best way that we've got to do that is to go through, plot out the data, and see what we've got. So if I take a look at this one here, I've got a bit of a curve that's going up. What does it look like? Well, kind of, sort of looks like it might be in that form of a parabola. Second power. Okay. So, now I'm going to show this to you, and if you are told to use this, I'm going to show you a couple ways of dealing with this. Now, one of the reasons why, if you're given these points, that this really, it works if you're only given these 3 points and it's just those 3 points. Now, you could go through and set up the equations. I'll show you how that goes. Way of dealing with that. So, here. Now, in order for us to deal with this, you got to set these up into the equations. Now, these are identified. We got some constant, if you want. C would be equal to, I don't want to do it that way. Ax squared plus bx plus c is equal to 0. Now, when we got a function and we want to see what we get out of it, we plug something in, we get something out, right? That's the way that these things work. Now, if I go back to where it says on here, it's a little bit bigger, you'll see that they put this in. If I put x into it, whatever the a and b, it should come out to be 13, right? Does that make sense? So when I am looking at this, what I would do is for the first equation, I know that if I put 5 in, it's got to equal 0. So that means that I'm going to have an equation that looks like this. A times 5 squared plus b times 5 is going to be equal to, what does it say it's supposed to be equal to? I did that wrong, didn't I? It's one of those things. What should x be? 0. Right? That's it. If you're going to make a mistake, you must make a good, obvious one. Right? Okay. So if I go through and do that, do I know what c is equal to? Fairly simple. I have no choice but to conclude that c must be equal to 5. Now that I've got that piece of information, I can kind of help myself out. Now, mind you, this really isn't a good example of this because they give you the 0 here and the 5. They tell you what the y-intercept is going to be. Generally speaking, what you end up having to do is you end up having 3 equations with 3 unknowns and use elimination and substitution to go through and solve. Kind of a pain. If I set up the next one, I know it's going to be a times 4 squared plus b times 4 plus, what's c? 5. And this has to be equal to what? 13. Now, last one would be there if I had a and negative 2 squared plus b times negative 2 plus, what's C again? 5 is equal to 25. Now, we can go through and do the algebra on this stuff. We end up with 16a plus 4b. Oh, let's say we can swing that over there, is equal to what? What's it equal to? And here we would end up having 4a minus 2b is equal to 20. Again, we can go through, try and figure out ways of dealing with this, and for the purposes of elimination, I'd multiply this equation through by a 2. So I end up with 8a minus 4b is equal to 40. When I combine the two together, I end up with 8 and 16 gives me what? 24. 4b, negative 4b cancels out. This turns out to be 48 divided by 24 divided by 24, and b turns out to be equal to 2. So now that I know that b is equal to 2, I can plug that into one of these other equations, go through and figure out what a is equal to. So if I wanted to, I could put it in up over here, and then I'd end up with 16a plus 4 times 2 is equal to 8. That means 16a would be equal to, subtract that 0, so a would have to be equal to what? That can't be. Would you see 24a? That one here is 16, because I was looking at this one up over here. Yeah, 24, like 24b, yeah. 16 and 8 is 24. But see, I took this equation here and plugged b into it as 2. And that's supposed to be 8. Even if I subtract 8 to both sides, that gives me 0. Oh, I just wanted to double check. It says a is equal. Ah. Yep. Duh. Too many things. A is equal. It makes a lot more sense now. Because if I go 16 times 2 plus 4b is equal to 8, that's 32 plus 4b is equal to 8. Subtract 32, and I end up with 4b is going to be equal to negative 24, so b is equal to negative 6. Okay. Do you see what can happen? Get mixed up with a variable or a number or a sign, and we end up making errors. And mind you, this is the simple one. Why? Because, like I said before, they wouldn't set that equal to 0. This is how it was done back in the day, before graphing calculus. Do you know how to do this stuff? Yes. Is it necessary? Not really. So, part of the reason that this isn't going to be required is if I've got something like this and I want to go and generate a formula for it. Now, the first thing it says here we're supposed to do is create a scatter plot. Now, regardless of what we do, we always want to go through and do that scatter plot. So, I've got how many pieces of data here? Well, I got 1, 2, 3, 4, 5, 6, 7. I got 7 pieces of data. The method that we have for trying to solve this, to determine what something is based on how many points. How many points? 3. If I've got 7 pieces of data, and I can only use 3 points to generate the equation, First question is, which 3 points do I use? You see how all of a sudden we're letting go a lot of data? When we take a look at this, and I got a graph on the graph here, does the line or does the curve of that equation actually hit all of them? The answer is no. So in this idea, I want you to go through and use the graphing calculator to generate the equations. You can do it manually, but if you do it manually, I can almost guarantee that everybody in here is going to have a different answer. The equations will be similar, close to each other, but not everybody is going to go and choose the same 3 points. So, that being said, let's get to the good stuff. Okay. This table shows the dollar amount or projected value, dollar value of the U.S. Internet mobile advertising market from 2006 to 2012. Okay. Create a scatter plot of the data. Now again, we've talked about this idea of after a certain period of time. This is after the year 2000. So, grab the calculator. Time to have some fun. Okay. So, stat, edit. Again, what we want is just the year after. So, my Y data is going to be 6, 7, 8, 9, 10, 11, and 12. 11 and 12. So I got all the pieces in there, 6, 7, 8, 9, 10, 11, and 12. L2 gets this. Now, we have to remind ourselves that this is going to be in terms of billions. So we've got 0.045, 0.114, 0.114, 273, 409, 5, and 1.023. Okay. So I've got my data entered. So, first thing that I'm going to do is I want to turn on my plots. Now again, up on the whiteboard, left-hand side there, it says to plot. It gives you the information. So, we hit the second key, Y equals. I want to turn the plots on. So all I'm going to do is press enter once. It's flashing on the on, press enter twice, and now that is. Window. We've talked a lot about window. What do we want to see? What should we set for the graph? Well, we're talking about the years from 2006 to 2012. Does that mean I put in 2006 to 2012? And the answer would be no, because we're graphing it after the years of 2000. So I'm going to set my window here at 0, and I am going to go up to 20. Why 20 and 0? Well, I probably am going to have to take a look at something beyond it. Maybe, I don't know. I wouldn't want to put it just at 6 to 12, because I like seeing a lot more of the picture of them, see what's going on with it. Now, why minimum? Of course, I'm going to set that to 0, But what should be my maximum here? Well, if I take a look at the values that I put in for y, the largest one was 1.023, but not in billions. The reply comes in billions. So my window here is going to go up to 2. And we hit graph. So now, we have this here. You see that? Does it sort of kind of look like a curve? Kind of looks like it's half a parabola. So I've done the A part here. I've created that. And now what I want to do is I want to find that quadratic function. So what I end up doing here is I am going to go stat, calc. So what do I want? I do not want linear regression, and look at number 5, quadratic. Exactly what we're looking for. So we're going to go down here to 5, press enter. Depending upon the software you may have to enter and go down a ways. Or tell it to calculate. So now, do I have an equation based upon the data? And what I like about this is based upon all of the data. So now if I'm going to go through and graph this, well then I should, and I still got to do a little research on this one. I got to figure out how in the world. I know that there's a way of taking this data, transferring it to the equations. I just don't remember which one it is. So this would be set up as y is equal to, and of course you should always write this down anyway. 0, 1, 4, 9, 3 significant digits, x squared, and then let's see, then this is going to be minus 0.105x plus 0.1372. Yep, actually that should go to 2. That should go to what? Y equals 0.0149x squared minus 0.105x plus 0.1373. Okay. Now a few more things. As I look at this graph, I see it's not a half bad fit, is it? But I see something else on here that puzzling. See this right down here? Now, I want to talk about this idea of interpolation and extrapolation. Interpolation is used to identify data within the data set. So if I wanted to know, for example, let's see, go back here to the information. If I wanted to know what it was in 2010, or not 20, okay, 6, 7, 8, 9, 10. I've got the years consecutively. If I wanted to find out something that was halfway in between, you know, like, what about July of 2007? I could do that and come up with a value for that particular month. It would be possible. But is it possible for me to really come up with a good answer as to what was going on in the year 2000 based upon this data? Well, if I took this data and said, hey, this has got to be the model, this has got to be the way it is, that means the advertising was up here, then it dipped down, there was negative advertising, and then it started coming back up. This is only good for that data. All it's good for. Because if you take a look at this mobile internet market, well, how much of a mobile internet market was there in the year 2000? Not much. So these are always things to keep in mind. Now it says graph the aligned data. Yeah, seems reasonably fit. Now it says use the model to find the year in which the mobile advertising market is projected to reach 3 billion. Now when I set my window, I only set my window as a max of 2. So I'm going to have to move this out here, and I'm going to put my window here at a max of 4. Graphic. Now, we've talked about this before. I'm going to go back to my y is equal to, and here I'm going to put in a 3. This is the quickest and easiest way to go through and figure out what is going on with this. So, graph it. Now all we got to do is, does it actually intersect? And the answer is yes, it intersects. So, I did the second calc. I want to find 5, the intersection. First curve. Now mind you, make sure that you are on an equation. So you hit enter, enter, yes, and it comes up with 17.8. So that would probably mean somewhere, but what's 8/10 of a year? How many months would be 8/10 of a year? Probably right around November, first part of November, end of October. In the year 2017, we end up getting 3 million. So, that's how it gets used. So, the nice thing is about this, it all works pretty much in the same way. You are going to get real data. Make sure that you identify the years that it's supposed to be after. The equation is always, they're always going to give this to you, where they want you to go and work with it from. So, put the data in, plot it. Come up with your equation, graph it, and then answer the questions. Now, I could show you how to do this again in a spreadsheet, but again, a spreadsheet is a kind of on the clumsy side. It has some advantages that you have a little bit more flexibility in what you're working with, but not necessarily speed. It takes a little bit more. Okay. Now, this is something that you should make sure that you go through and read. Comparison of linear and quadratic models. Now, when we take a look at data, we sometimes want to have a quicker and easier way of determining, do we use a linear equation, do we use a quadratic, what do we do? Well, if we go and take a look at the data, and we have our X data incremented by a specific amount, could be going by 1, could be going by 2, you should be able to take a look at the Y data, and it should be going the same thing. It should have a constant increase. Remember, a linear is always going to be having a slope. Always the same amount of rise, always the same amount of run. So if I take a look at this, and they use a spreadsheet to calculate this. So a time index, 1, 2, 3, 4, 5, and 6, is going up by the same amount. The height. First difference is 49. So the difference between these two is 49. Then it goes to 29. Then it goes to 9. Then it goes to negative 9, negative 29, negative 49. So when I take a look at this and I see that the differences are not uniform, I know that this will not be linear. When I take a look at the second differences, I see that the second differences are all the same. The second differences lead us to the fact that, okay, this is a quadratic function. Now, depending upon how much data you got, you're going to have to plot it anyways. But there are times when you take a look at the graph or the plot that you've made, and you can't distinguish between whether it is a line or a curve. If I kind of go back to what I had here, depending upon the window, if I were just to look at it from, say, this point on up over here, does that look fairly straight? So if you cannot determine whether or not you have a curve or a straight graph from the data, you're going to have to go and take a look at first at the differences. If the second differences are basically the same, quadratic. Power functions. Same idea again. Power function, they give us the information here, we go through and do that. Okay. So, let's take a look at this. When you take a look at the data, what does it strike you as to begin with? Do you think curve? Do you think line? Do you think something else? Well, we've got it graphed out here. We're kind of looking at it. It does kind of look linear, right? That's kind of what the implication would be. Now, again, we got real life data, so things can be a little off with it. Perfect. So, they come up with a power model because they asked for it. So they put the data in just like we would normally do. We go and ask for the power model, and we go and hit the buttons on that, and away we go. Easy enough. Give it a try. So, grab your calculator. And I've actually found resetting it's almost the easiest way to clear out everything so you can start fresh again. They want this for the number of years after what? After 2000. So, edit. First piece of data. Once you get all that stuff in there, put it for L2, your percentages. Again, make sure that everything lines up so that all your X data and all your Y data go in there and you've got them all set. Okay, so second Y equals, if you shut it off and reset, got a stat plot, turn that back on, window. Now we're going from the year 2000, so we'll put in 0. And we're going out to the year 2050, so I'm going to go out to 2060, so I'm going to give it another 10. Scale is at 1, minimum, 0, maximum. What is the largest possible Y value that I can get? Should be easy. What? Well, 34 is the largest they give me. But what would be the largest Y value that I could ever possibly graph with this thing? Say 100? 100. We're talking about percentages here, so the biggest value that can be is 100. So let's graph and see what we got. Okay, see the data there? And there we go. Although having 100% of the population with being diabetic, that wouldn't be a good thing, would it? Must be impossible. So, question here is, in what year does the model predict the percent to be 29.6? So, go back in here. We can go y is equal to, and, well, we need an equation for that first, don't we? Because I could put in 29.6, hit the graph, and I see that it's going through there. But my question for you is, does the data give us 29.6? Not really. I know it's going to be right around 2035, but that's 2035 and that's 2040, so it could be 2036. I don't know. So, we go to stat, we go to calc, and we're supposed to have which one now? Power, so we go down, we can keep going down, and there we go. A, power regression. Enter, enter. So now I've got a power regression. A is going to be equal to, let's see, should probably write that down like we always are supposed to do. So we've got y is equal to 4.947 x to the 0.495 55. So, equals, go down here, let's see, 4.947 x to the 0.4955. Okay. We got that there. Now, since we're dealing with things that are on the low side, would it make sense for me to go and say, you know what, I'm going to go up to 50 here. Change it out so that I can see a little bit more definition of my graph. Is that realistic to do? It's definitely. So, I go and hit second trace, 5. Make sure that I am on the data. First curve, yep. Second curve, yep. And it says at 36.98. So it was basically in the year 2036 in December. I know why that is, all that Christmas candy and stuff. Halloween candy is all set in. But there we go. We've got it. Information that we need and how we can interpret it. Again, this idea isn't all that difficult to deal with. Okay. Now it does talk about here which ones are which. Found a power model that is a good fit for data, but a linear function or quadratic function might also be a good fit. Now it says a quadratic function may fit data points even if there is no obvious turning point in the graph. If the data points to peter or rise or fall more rapidly than a line, a quadratic model or a power model may fit the data well. In some cases, it may be necessary to find both models and determine. Now, I realized that when we were doing the linear stuff, there was a correlation coefficient that gave us, how good of a fit. That doesn't really work all that well for us here. And a lot of times it is just simply going through, grabbing the equation, putting it in there, seeing what works. So, here they give an example of this. They went and used a spreadsheet for this one. It's a little bit easier because of all the data that we've got here. Find a quadratic and a power function. So they got that, they've got the functions there, so they got the data there. So the question I have is, which one is a better fit? The one on the left The one on the left side there, got a quadratic model. It fits some of the points. Doesn't really look like that good of a fit when you start getting further out in the years, does it? Better fit earlier. What about the other one? That one fits really nice after 20 years, doesn't it? It's not so much to begin with. So, which one's better? So I'm going to let you guys there, and I'm going to let you start working on the assignment we do at the end of class tomorrow.